Today we're going to continue looking at Unit 2 with deductive reasoning and conditional statements. Deductive reasoning is when you are using facts, definitions, accepted properties, and the laws of logic to form a logical argument or conclusion. We will be using deductive reasoning as we write proofs in this unit. Conditional statement is a logical statement that has two parts. It has a hypothesis and a conclusion. The hypothesis begins with if, and the conclusion begins with then. Here are some examples. If a quadrilateral has four right angles, then it is a square. If we want to identify the hypothesis and conclusion of this conditional statement, it says to underline the hypothesis once and the conclusion twice. So the hypothesis is the part that follows the word if. So a quadrilateral has four right angles is the hypothesis. So we're underlining the hypothesis one time. And it says to underline the conclusion part of it twice. So the conclusion is going to be underlined twice, and it says then it is a square. So the conclusion part is it is a square. What is the truth value of this statement? That just means is it true or false? So I'm going to read it again. If a quadrilateral has four right angles, then it is a square. Well, for it to be true, it has to be true all the time, 100% of the time. And I know of a quadrilateral that has four right angles that is not a square. So the truth value here is that it is false. It is false. And often when we have a conditional that is false, we will ask you to provide a counter example. A counter example will keep the beginning of the statement true and make the conclusion false. So we're looking for an example of a quadrilateral that has four right angles but is not a square. And that would be a rectangle. So for providing the counter example, you could either state rectangle, or you can draw a picture of a rectangle. But if you are drawing a picture of a rectangle, you need to mark it properly where we will know it's a rectangle. You can see my drawing is not perfect. But rectangles have four right angles, and they have opposite pairs of sides that are congruent, but they're not all four congruent. So I'm using congruent markings, different markings on the top and the bottom that do not match the ones that I have on the left and right side. So that's how I can draw a picture of a rectangle, or I can say the word rectangle. It is a specific case that keeps the hypothesis and makes the conclusion false. That is what a counter example does. Let's look at some conditional statements and sort of rearranging them to create new statements. We have the converse. A converse is when you are switching the order, and so the order will change to have if conclusion, then hypothesis. So the converse is when you switch the order. And so I'm going to just put here as a little note, if conclusion, then hypothesis. It's basically the backwards version of the statement. Sometimes the wording will need a little bit of adjusting when you are switching the order. Also, the hypothesis often contains like the noun of the sentence, and then often at the end uses words like it, like in this one here. We have the word quadrilateral at the beginning and the word it at the end. You'd probably want to keep those words where they are. If I was writing the converse to this phrase at the top here, I would have said, if a quadrilateral is a square, then it has four right angles. So noticing how you are kind of keeping the noun at the beginning and the pronoun, I think is the word for that, at the end. So switching that order, and again, sometimes the wording is changed. If both the conditional and the converse are true, you can combine them as a special statement called a biconditional. Oops, that is the highlighter, not the pen. A biconditional is written specifically to have the phrase if and only if in the middle. It will not have the word if and the word then where they traditionally are in the conditional and the converse. So here we have an example, and where they give you the example, that first line there, this is the conditional statement, okay? That's our starting statement. We are going to decide if it's true or not. We're going to write the converse and decide if that is true or not. If they are both true, then we will be allowed to write the biconditional. That just basically means it's true forwards and backwards, and it has a certain kind of phrasing. So let's look at this one. It says, if a triangle is a right triangle, then it contains one 90-degree angle. So the converse to this, we're going to keep the noun at the beginning, a triangle. So that's going to stay where it is, and the word it is going to stay where it is. And we're going to flip the is a right triangle and contains one 90-degree angle. Those parts are going to get flipped to make the converse, that switching of the order. So we're going to say if a triangle contains one 90-degree angle, I use degree symbol instead of the word, then it is a right triangle. So I wrote the converse. I didn't decide if this was true or not, so let me go back to the conditional. If a triangle is a right triangle, then it contains one 90-degree angle. That is true. That is a true statement. Right triangles have exactly one 90-degree angle. Reading it backwards, if a triangle contains one 90-degree angle, then it is a right triangle. This is also true. This is basically because this is coming from the definition of what a right triangle is, and anytime you have a definition, it can be written as a biconditional. So the conditional is true, the converse is true. Since they're both true, you can write a biconditional. If either one of them was false, you would not be allowed to write a biconditional. And the biconditional will be to write the hypothesis part, then the phrase if and only if, and then the conclusion. So it's going to say a triangle is a right triangle if and only if. That's the main phrase there. It contains one 90-degree angle. So again, the important thing here, biconditional has this if and only if phrase in the middle that is going to be joining the hypothesis and the conclusion. You are only allowed to write it if your conditional and your converse are both true. One way to abbreviate the phrase if and only if is to write IFF. Now be careful, because you need that second F in there, otherwise you're just writing the word if. So you can abbreviate it that way, but be careful, make sure you are accurately doing that, because if you just put the word if, it will be marked incorrect. Negation. The negation of a statement is changing it. If it said something is, you would say it isn't. If it said it isn't, you would say is. So just really switching it's not necessarily opposites. It's not like up and down. It's like up and not up. Because you could go left or right. So you're just saying it's not the thing that it currently is. So most of the time you're going to see something is, and you're going to switch to isn't, or is not, or you might say isn't. If I could write and then you might switch to is. Okay, so just kind of going back and forth there. So here are a couple of examples. It is hot outside. It isn't hot outside. If it isn't humid, and we want to negate that, then it is humid. Some people say it isn't not humid. I would also accept that, although it's strange, like double negatives, it gets weird. The inverse, so we looked at a conditional, that's your if-then phrase. We looked at the converse when you switch the order. The next main one is the inverse. And the inverse of a conditional statement is when you negate the conditional. So you're keeping the order, but it's negated. I like to think of this as the not. The converse I like to think of as the flip. So converse, you flip the order. Inverse is the not version. It's the negated version. And contrapositive is our other one that we're able to write. And this is when you both flip it and negate it. So the contrapositive is pretty much the negation of the converse. So there's a lot of them. It's a little hard to remember them all, so you want to practice them. So this is to negate the converse. So my nickname, flip and not. So that just helps me to remember them. So you have your conditional, your original. You have the converse, which is where you flip the order. You have the inverse, which is when you negate this whole thing. You negate the hypothesis and conclusion of the original statement. And the contrapositive is when you flip the order and you negate. So you could also take the converse, which is already flipped, and negate it. So I'm going to be practicing that using the following conditional statement. We're going to write its converse by conditional if possible. Remember, they have to be true at the beginning and true for the converse for that to happen. And we're going to write the inverse and the contrapositive. So we're going to practice all of them now, and they just take practice. Right now you might be thinking, what has she been talking about this whole time? But practicing them here is going to help us. So we have a phrase, if a polygon has 3 sides, then it is a triangle. If we have a polygon and it has 3 sides, that is a triangle. That is true, so the truth value is true. The converse would be if a polygon is a triangle, then it has 3 sides. So just switching the order, but again, we're going to keep the noun at the front of the statement so it makes more sense. The polygon is a triangle, then it has 3 sides is true. Since these are both true, we are able to write the biconditional. So we're going to take off the if and the then, and we're going to join the hypothesis and conclusion with the phrase if and only if. So a polygon has 3 sides if and only if it is a triangle. And this is true. Now for the inverse. So the inverse is taking the original order, a polygon has 3 sides, then it's a triangle, and we're negating it. So instead of the word has, we're going to say doesn't have or does not have, and instead of is, we're going to say is not in that conclusion part. So we're going to say if a polygon does not have 3 sides, then, don't forget the if and the then. Those are probably the most common mistake because people forget them. It isn't a triangle. And that would be true. And again, like they're going to be all true when you're using a definition as your conditional like we are here. But there will be some that we are not using a definition so that we can really test you on, is it true or false, and the phrase counterexample. So they're not always all true. Contrapositive is flipping and negating, or you can go look at the converse and just negate that. So the converse was a polygon is a triangle. Then it has 3 sides, where we're going to negate that part. If a polygon is not a triangle, then it does not have 3 sides. And this is also true. All right, so we practiced them all. We're going to be looking at a couple of other things. These are point, line, and plane postulates. We've already seen these when we studied vocabulary, but just kind of to reiterate again, through any 2 points, there is exactly 1 line. A line contains at least 2 points. That's kind of a forwards and backwards of the same idea. If 2 lines intersect, then their intersection is a point. Through any 3 non-collinear points, there exists exactly 1 plane. That was just kind of left off there. A plane contains at least 3 non-collinear points. Of course, they have more, but at least 3 and non-collinear, and that's how it's sort of defined. If 2 points lie in a plane, then the line containing them lies in the plane. And if 2 planes intersect, then their intersection is a line. We're going to be looking at a couple of sort of special cases here and drawing some sketches. If M is parallel to N and N is parallel to K, then, so notice we have parallel lines that are parallel to the same line. Then we want to conclude that they are also parallel to each other. And this is, we're going to look at and see if it's true all the time. And we're going to be sketching it and determining if this is a true statement. So when you are looking at these, one thing to keep in mind is to think on, sorry about that. Think on if it is all in a plane together, and then think on if it was 3-dimensional and they're not necessarily coplanar, because they did not say that these lines are all in the same plane. So we're going to sketch the scenario. If we had this in a plane together, let's draw a plane. And if M is parallel to N, that means that they are facing the same direction. They're never going to cross. They have the same slope. And if N is also parallel to K, well, then M and K will also be parallel. This actually has a title. It's called the transitive property of parallel lines. So when they're coplanar, that is working. Let's look at 3-dimensionally. So I'm going to start by drawing like a rectangular prism here. Okay, so kind of visualizing in 3D. And let's say that this is M and this is N over here. And let's put K in a different plane. So I'm going to make K be this bottom edge. Well, M and N are parallel and they're in that top plane, and N and K are parallel and they're in the side plane there. And if they are parallel, then we can also conclude here, we can look at M and K and see that they are also parallel. They're just sort of diagonal from each other in this image, but we could sort of draw a plane that's connecting those 2 edges, and those lines are parallel to each other. So this works in 2D and in 3D. And so this is always true. Like I said before, this is called the transitive property of parallel lines. Now we have another scenario to think about below here. It says if A is perpendicular to B and B is perpendicular to C, and what we want to see here is A parallel to C? So we're going to be looking again kind of 2D, 3D, and see if we can come up with a counter example, because I'll tell you it's not always true for this scenario. So if we wanted to consider if they are coplanar. Now if they are coplanar, this is actually going to be true all the time. But if they're not coplanar, it's not necessarily true. So we have B, and B is perpendicular to A and C. So I'm going to start by drawing B, and I'm going to draw A and C perpendicular to it. There's A and C. And if A and C are perpendicular to the same line in the same plane here, like so, they would be parallel. So it's true for this image. But if we go three-dimensionally, then it can be false. And I'm going to show you sort of two diagrams of this in 3D where it will make this a false statement. So in this situation, we could have, let's say that B is over here on this edge. That's B. And let's say that this is A. And we can see that they are making a right angle in that corner there. And we could add C perpendicular to B. We could add it in different places, but one place that I kind of love to put it is right here on the front edge. Either go on the front edge or the back edge. If you put it on the front edge, it's actually perpendicular to B as well as to A. So there's like all of these making right angles and meeting at this one point. So it doesn't make them parallel to each other in my sample. If we had put C along the back edge, it wouldn't cross A at all, and that would then make A and C a pair of skew lines where they're never going to intersect. Another way we could draw this example is if I draw a plane here and I draw B and I start with A perpendicular to B like I had earlier. And these two are coplanar, but then if I add in line C so that it is not coplanar, where you can see it goes dashed and then it's going down underneath the line. And so it's basically like you took the picture from the far left and you took line C and you twisted it up out of the plane, and since they are not coplanar, they cannot be parallel. So over here in these images, it's not true. So counter examples, my diagrams here and here are both counter examples. They prove that if A is perpendicular to B and B perpendicular to C, then not necessarily A and C ending up parallel. So I'm going to add little parallel markings to that first diagram there. There we go. If you're ever having to draw these images, be sure that you have proper markings, like if you need the parallel markings, they're there, or if you need those right angle markings. We were having to sketch perpendicular lines because that's the hypothesis, so we absolutely need those right angles in our drawings. And then we just have this little bit of this looking at this diagram to complete our day 2 notes. So concept, summary, interpreting in a diagram. We've looked at this several times before. If you interpret a diagram, you can only assume information about size or measure if it's marked. So be sure you're not making assumptions. The things that you can assume, okay? So looking at what we can assume and what we cannot. All points in this image are coplanar. As you can see, there's no dashed areas. There's nothing to indicate 3 dimensions here. They named angle BHD, and they're looking for a linear pair. So BHD is like this little angle here that I'm marking in. So a linear pair to it could be either the angle below it or this angle over here to the right. I am going to go with DHF, that angle to the right. The next one is talking about BHD, so again, that one there, and they want vertical angles, so vertical to it would be this one down here, and so I'm going to say angle AHF. They said point A, H, J, and D are collinear. As you can see in the diagram, they do have a line drawn connecting them. And line AD should have this symbol, and BF are going to intersect at point H. We can see that in the diagram. If you locate those two lines, they do intersect at H. Things that you cannot assume. You cannot assume that GF and E are collinear. So if you look in the diagram, G is here, F is here, and E is here. They do not have a line connecting them. So since there's no line and there's more than two, you cannot make that assumption. If there was only two, G and F, yeah, they're collinear because any two are collinear. Next, we cannot assume that line BF and CD do or do not intersect. We don't know if they're parallel. We don't know. We can't see the intersection. We can't make any assumptions. Also, we do not know that BHA and CJA, which would be, BHA is down here, so this angle right here, and the other one they said CJA is up here. We don't know if those are congruent to each other. We don't have any markings in the image to allow us to know that. And we also don't know that line AD and BF are perpendicular. And we don't know if we have any right angles because there's no markings to tell us that. So those are things you do not want to assume from a diagram. All right, and I think I guess I'll finish this part too. Oh, these notes are quite long, sorry about that. Which of the following statements can and cannot be assumed from the diagram? So the same kind of idea. E, D, and C are collinear. If we look at the picture, we can see the line that is containing E, D, and C, although part of it is dashed. That's just trying to show you that that's the part behind the other plane there. This is a true statement, so we're just going to do this as true, false. The intersection of BD and EC, let me find BD and EC, that is here, crossing here. It is D, that is also true. We do not have any right angle markings, so as far as things being perpendicular, we cannot tell anything is perpendicular because there is no marking. So those are false and false. All right, so that is deductive reasoning, which is mainly like the diagram stuff that we were doing here, and conditional statements, which is the conditional, converse, inverse, contrapositive, and then sometimes that biconditional statement.